So let's explore the two distributions that we've been talking about so far. We have the z, or normal distribution, and we have the t distribution. And you're probably still wondering, well, which one do I use? Well, the short answer to this that's going to help you out in this class is if we're working with proportions, we're going to be using the z. If we're working with means, we're going to be using the t. And when do proportions arise is when we have categorical data, because it's asking, oh, what percentage or proportion fall in a certain category. When do we use means? Well, that's when we're working with quantitative data. We have numbers because we can calculate a mean when we can add the numbers and divide to find the mean. So that's the short answer. But then you're probably asking, well, when we first started learning about this stuff a couple modules ago, we had to sometimes use the z distribution for means. And that's true. The z, in some certain special cases, does apply for means. But what are those special cases? Except. Well, the reason why we could use the z sometimes for means is because we know something specific. And what is that something specific that we know? When our standard deviation of the population, sigma, so the population standard deviation, is known. If in that rare case we know the population standard deviation, then we can actually figure out all of our things using the z distribution. And so sometimes this comes across where, they tell it to us, like, hey, use this as your population standard deviation. Great, we'll use the z. Or just like that, a lot of times in our sample size problems, they're giving us some value of the population standard deviation that we're going to assume to be true. So then we would use z. But almost all other cases, that's when we're going to be using t. So this will almost never arise when we use the z, because we're often trying to figure out, what does the population mean? Or is this true about the population mean? So how could we actually know the population standard deviation, if we don't know the population mean? When to calculate it, you need the population mean. So this is a rare case when the standard deviation is known. Right? The sample size formula, we will be using it. So that's why it's for this class, the way to move forward is if we have proportions, we're going to use z. If we have means, we're going to use t, because the population standard deviation will almost never be known. We're always just going to use s as our sample standard deviation. So now let's talk about when this t arises to help you out. But if you didn't get anything else, that's the key thing that you want to think about moving forward. So why do we end up with the t distribution? It all happens to be because of that unknown value of sigma. That gives us a level of uncertainty. It adds another thing that might change and add more variation to our statistics. So let's think about it. Going back to our central limit theorem, the key thing that we actually learned was that the distribution of means, if I look at the distribution of sample means, or sampling distribution of means, of all these x bars, what we found is that if I take a sample mean, we'll get, or take a bunch of sample means, what we can find is that if we started taking and creating a plot of these means, that the center of all of these means would start stacking up towards some center. And what is that center it's going to be stacking up to? Well, our sample mean will actually be around our population mean. Not only that, but it'll be this bell-shaped curve that actually becomes the normal distribution. And that is our central limit theorem, is that the distribution of x bars, or of sample means, is normally distributed, centered around our population mean. Not only that, but we actually know the standard deviation. So we can find also that the standard deviation of these x bars could be calculated by taking the population standard deviation divided by the square root of our sample size, n. And so if we were to do the central limit theorem, it follows the z distribution, where a z-score, if I wanted to see what's the probability of getting some x bar greater than or equal to some number, well, we can find that specific x bar and find its z-score. How far away, how many standard deviations away is that x bar from the mean of all the x bars? Well, the mean of all the x bars is the mean itself. And then we can divide by the standard deviation of all the x bars, and it'll give us a z-score, because that's where the z arises. It's just how many standard deviations away it is. But as we've seen, the z-score for x bars, what is the mean of all the x bars? Well, it's just the mean of the population. And what is the standard deviation of all the x bars? It's just sigma over the square root of n. So as we've seen, again, the sigma is in this formula because we know the population standard deviation. It follows the z distribution. It follows a z-score. But as soon as we switch that out, say I don't know the population standard deviation, and I said, all right, let's still try to figure out what we think, how many standard deviations away it is, and switch this to s, our sample standard deviation. Well, there's more uncertainty there, right? That s could be a big s, it could be a small s, I don't know. We have to account for that. And what helps us account for that is a wider distribution, one that's not as certain, which gives us our t distribution. So again, when does that t arise? Is because of this. We know the sample standard deviation, s, not sigma, the population s standard deviation. That's when we use t, because this is unknown. The sigma is unknown. We switch it to a sample standard deviation. Now it follows a t distribution. So now, one of the things that you may be asking is like, okay, I saw maybe like on a Khan Academy video, it says we use the t distribution only when it's a small sample size. Well, that's not wrong, but it's not the full picture. So let's take a look at why we can use the t or the z distribution when we have a larger sample size. So in this case, I know Khan Academy likes to say n is at least 30. So one thing about the t distribution is it's actually the same shape. It looks bell-shaped. But there's actually a lot of t distributions. It depends on our degrees of freedom. And remember, our degrees of freedom is just the sample size minus 1. Well, one thing about the t distribution with our degrees of freedom is the more degrees of freedom we have, meaning the larger sample size we have, the closer it looks to the z distribution. Well, how close does it get? Well, according to Khan Academy, if we do 30, then we are going to be close enough that we can use it. And for me, though, it's like, if we can be more accurate, let's be more accurate. So we'll just always use the t distribution. But let's go and explore that so I can convince you. If we have something like a z distribution. So here we have the normal z calculator because it's a mean of 0 and a standard deviation 1. And I want to find a critical value for 95% confidence. Well, I can type in my 95% here, and that's where it gives me 1.96. So if I'm 1.96 standard deviations away, I will capture 95%. On the other hand, if I wanted to be 95% confident and use the t calculator, well, it depends on our degrees of freedom. So let's say we had a sample size of 11, and 11 minus 1 is 10 degrees of freedom. Well, if we type in 95 here, we have to use a t distribution score, a t critical value score of 2.2281. Notice we had to go farther out. We had to go 2.22 over 2 standard deviations away versus this is less than 1 standard deviation away. Why? Because of, again, the uncertainty of s. We have to account for that, so it goes out wider. Now, what if I had a larger sample size? Let's just say, as Khan Academy says, let's say we have at least or more than 30. So if I have 31 as my sample size and a degrees of freedom of 30. Well, let's see what it gives us now. 0.95. It tells me 2.04, so it's a lot closer. It's a lot closer. It's only off by 0.08-ish, a little over 0.08. And so that actually might be enough for us to be like, all right, that's close enough. I will use the z instead. But again, for me, and also probably for your homework problems, it's better if you just use the more conservative value of the t calculator. Because since s is unknown, this is the actual since sigma is unknown and we only have s, this is the more accurate value. So how many does it take before we actually can match the z calculator? Well, it takes an infinite amount. So if we actually start seeing and looking at higher degrees of freedom, let's try 100. We see it gets pretty close, 1.98, still off by a little bit. If I make this 10,000 and type in 95%, There we go, 1.9602. Still a little bit off from it, but 9602, that's basically right on. Right? So it requires a large sample size before it matches up exactly. When we have at least 30, sometimes we just say, oh yeah, it's close enough for us to use. But to be safe, let's just always use the t whenever the sample standard deviation is given and the population standard deviation is unknown. Right? So that's the idea, is the t distribution is for means, the z distribution is for proportions. Now, why is the z distribution is for proportions? Let's just remind you of that really quick. It's because the sample proportions are also going to be approximately normal, right? So they'll start building up here, and then in the center of all these, it'll start building up towards the center. And what's the center of all these p hats? Would be p itself, the true proportion. But now what's the standard deviation of these p hats? Well, this does not depend on the data. It would depend on p itself. We can actually calculate the standard deviation using the formula. So since we can calculate that standard deviation and not use an unknown sample standard deviation, we are able to use the z still. It's going to be close enough for us to be able to use the z. And so that's why the proportions, we're always going to use the z critical values. And for the means, we're always going to use the t critical values.